তো মলাদা আপনার অনেক ছাত্ররা কিন্তু দারুণ দারুণ পজিশনে আছে সব।
আমি ভালো, এই মেয়েটি এখন খুব ডিউকেজে রেবেকা স্পোর্টস ও রানিং হয়ে রিসেন্টের মধ্যে পুরো রিসেন্টের মধ্যে 2022 পেয়েছে।
ইমান ইমান
হ্যাঁ বলো বলো।
ইউটিউবে লাইভ স্ট্রিমিং শুরু হয়ে গেছে,
আচ্ছা
তুই শুরু করতে পারিস, তবে হরে কৃষ্ণকে আগে রেকর্ডিং শুরু করতে হবে। সুমন্ত,
হ্যাঁ বলছি। হরে
শুরু
কৃষ্ণ।
করা যাক তাহলে।
হ্যাঁ, রেকর্ডিংটা স্টার্ট করে দিই।
হ্যাঁ, রেকর্ডিং স্টার্ট করে দিচ্ছি, স্টার্ট হয়ে গেছে।
হ্যাঁ, রেকর্ডিং ভুবন শুরু করে দিই।
ওকে। We welcome all of you to this lecture series for propagation of statistics, education and research organized by Calcutta Statistical Association as a part of its outreach program. The association was established in 1945 by a group of statisticians who were members of the teaching staff of the Department of Statistics, University of Calcutta. From the very onset, the objective of the association has been to promote activities related to statistics. Using its limited manpower and other resources, the association continues to play a key role in developing statistics. This lecture series is being organized as a part of celebrating 75 years of CSA's glorious existence. The association has always focused on advancement and dissemination of knowledge of statistics through its various publications. The Calcutta Statistical Association Bulletin, from the very beginning, paid due attention to quality of articles. Today, the bulletin is highly rated by the international community of statisticians. Since 2016, Calcutta Statistical Association Bulletin is being published by Sage Publications. The association regularly organizes lectures by eminent scholars from India and abroad. Since 1991, Calcutta Statistical Association, jointly with the Department of Statistics, University of Calcutta, is organizing an international symposium on probability and statistics every 3 years. To know more about the activities of the association and to be a part of CSA, kindly visit our website www.calcuttastatistical.association.org, or you can mail us to Calcutta CALSTATA, that is calstata@gmail.com. May I now request all the participants except the speaker to kindly turn off your microphones. Please write your questions to the speaker in the comment box only. We'll have a discussion session at the end of the lecture. It's now time to introduce our speaker for today. We are really honored that to deliver the third lecture in this series, we have with us today Professor Maloy Ghosh, Distinguished Professor of Statistics, University of Florida, and former President of Calcutta Statistical Association. Professor Maloy Ghosh is a world-renowned authority on the theory of statistics and its applications. His range of expertise includes non-parametric inference, sequential analysis, decision theory, Bayesian statistics, and small area estimation. As a recognition of his seminal contributions, Professor Ghosh has received the prestigious S.S. Wilkes Memorial Award in 2020. Professor Ghosh very recently received an honorary doctorate from the University of Economics in Katowice in recognition of his outstanding achievements in the field of statistics and its applications. Professor Ghosh is an elected fellow of the Institute of Mathematical Statistics and American Statistical Association. Professor Ghosh is the author or co-author of over 300 research publications in the field of statistics and its applications, and is the advisor of over 40 PhD students. Professor Ghosh has been the editor of Sequential Analysis and the co-editor of Shankha. He has also served as the associate editor of American Statistician. Professor Ghosh has always been closely associated with Calcutta Statistical Association. We are grateful to Professor Ghosh for having readily responded at a very short notice to our invitation to deliver the third lecture in this series. May I now request Professor Ghosh to begin his lecture.
It froze. Something froze. Can you hear me? No?
Yes, sir.
Something
Yes,
froze.
yes.
Okay. So maybe time to start actually. Shortcut, if you can. Thank you very much, actually. Thank you. Thanks, everybody. Thanks for such a nice introduction, Himan. I really appreciate. I've been associated with the CSA for many years, and CSA has done a lot for me also for years. So it is a mutual thing. And I wish CSA further glory in the years ahead. So if I understand correctly, today's talk is meant for a wide audience, ranging from undergraduates to people who are doing their masters. And obviously I can see people who have been not only got their PhDs, but who have been around for such a long, long time in our profession. So it will be a mixture of kind of talk. At least the initial part will be very simple, bringing in the problem. And then the middle part will be some of the early history and very briefly some of the modern developments. Smaller estimation is a topic which actually people teach for a whole semester, and you can have material to teach beyond one semester. A very authoritative treatise is by J.N.K. Rao and Isabel Molina, the second edition of their book by John Rao. So I encourage everyone to look at it if you get interested in the topic. What I will do, I'll trace the history, early history. Next slide, please. So that will be the introduction. Synthetic estimation, that goes way, way back, actually. Then model-based estimation. Okay, I will one correction. I will only talk about area level models, but I won't be talking about unit level models at all. And up to that point, it is still we're talking about early history, part of the early history until say 1990. And more recent things, the last few topics, benchmarking, fixed versus random effects, variable transformation. And then I will give you a whole list of topics which I have not covered. And you'll find the number of topics that I have not covered actually is far greater than the ones that I'm going to cover today. And if there is any question, please feel free to ask, as Iman suggested, and I'll be very happy to answer the questions at the end of the talk. Thank you very much. So I will start with the introduction. Okay, next, please. So first question is, I'm sure most of you are not familiar with what small area estimation is. Some of you are. And for them, it will be the first few slides will be just a very boring thing, but let us do it for others. So it is some of the statistical techniques involving estimation of parameters, small subpopulation in a larger survey. So what is it? For example, if the survey was conducted at a national level, and then even the states can become the small areas because you don't have the resources to carry out another survey. You don't have the resources, the money, and whatever, manpower, whatever it is. So it depends on what a small area is. The definition could be, as I said, county, census tract, school district, they're common, but as I said, even states could be if the regional survey was conducted at a national level. It could also be a small domain, cross-classified by demographic characteristic, age, sex, ethnicity, etc. For example, you can think about the Vietnamese subpopulation or the Japanese subpopulation in a certain region, say Midwest of the United States, cross-classified by age, say several categories, say 5 to 17 or until 17, then 40 to 65, 65 and over, the school-going children, then the working population, and the retirement community in most part, things like that. So it's not just the area, but the smallness of the targeted population in an area which constitutes the basis for small area estimation. The smallness of the targeted population. For example, that's what I was trying to say. If a survey is targeted toward a population of interest with prescribed accuracy, the sample size in a particular subpopulation may not be adequate to generate similar accuracy. And you do not have the resources to carry out another survey. You have to use the results of the original survey to get the final outcome for this subpopulations to do inference. Next. The domain area is called direct based on domain-specific sample data. That's the direct estimate. And it is usually, domain is regarded as small if the domain-specific sample is not large enough to produce estimates of desired precision. That's all I'm saying. It may increase with the population size, but that's not always the case. For example, if you are talking about actually Hispanic population in certain mountain areas, the mountain regions of the United States, the population could be, even if the population of a particular state is bigger than the other, it doesn't help very much. Possibly the subpopulation will not be adequate. That requires the use of additional data. Nowadays, people use administrative data. With the advent of the word, buzzword is what? Big data in these days. So administrative data has playing a big role in small area estimation for years now. But the thing is, data from other related areas. For example, when you're talking about a county, I'll talk about my own state, Florida. We live in Alachua County, but we can use information from some of our neighboring counties, say Dixie, Gilchrist, etc., etc., etc. So resulting estimates are called indirect estimates because they borrow strength, that's the word coined by Tukey, for the variable of interest from related areas and time periods to increase the effective sample size. It could be over time, could be space and time, both. So this is usually done through models. Almost inevitably, explicit or implicit models, mostly explicit or at least implicit, that links, I will possibly give you one example of an implicit thing that links the related areas and the time periods. Next. Now, just a little bit of history. It has been used for a long time. Statistics in the 11th century England, 17th century Canada, they used some of such estimates based on either census or administrative records. And demographers have been using, of course, a variety of indirect methods. They don't use the term small area estimation, actually. Of population and other kind, nowadays they do, they did not, but they've been using it before even the term was coined, of interest in post-central years. For example, if there is a census in 2020, of course, in the United States, there was just one last year. When you go to 2028, the data may not be trustworthy enough to do any kind of meaningful statistical inference. So naturally, one has to use indirect methods. Now, there is one interesting thing. But legislative acts by national governments have created a need for that. My example, the one I'm going to say here is CSA. That's the one I was, data which I got on several occasions from the US Census Bureau. Small area income and poverty estimation mandated by US legislature. Next. So demand for the private sector increased because, of course, the business decisions that depend on local socio-economic conditions. So they need to get some reliable data or meaningful data for doing inference or formulating their policies. Let's call it that way. Economics in transition, that's what I was talking about. Central and East European countries, former Soviet Union countries, so they have now moved away from centralized decision makings. And sample surveys are used almost all the states. My own experience is with people in Poland for so many years, more than a decade now, and they are using small area estimates all the time for different purposes. And it is so also for other countries, say Latvia, Lithuania, and others. That's the one I know. I'm sure it is true for some of the other countries as well. Next. And some examples, hierarchical-based estimates of the overweight prevalence of adults. I'm not going to talk about it. Melek, Davis, and Cao, National Health and Nutrition Examination Survey. Then the second one is estimates of crop acreage. That is one classic example of a unit level model. I'll not talk about it. I'll just define it in one of the slides, but I won't talk about it because I have already enough slides for an hour. I may go over an hour. Please excuse me. Then income for small aces, pay period. That's a classic paper, not just because of the example, but because of the methodology. To my knowledge, that is the first meaningful model-based approach which was given. That has become a classic. The citations abound, more than 1,000, maybe a lot more by now. Then model-based county estimates of proportion of K to 12 children under poverty. I'll talk a little bit about the poverty thing. Estimation of median household income is a very important thing for formulating energy assistance program for low-income families. And it is here the states are actually the small areas, although nowadays they're using it for counties as well. And empirical and hierarchical methods, that's become very popular, defined small area poverty measures. This is a big thing now. It is the World Bank people first started. It is not Molina and Rao, but World Bank people did not use the kind of fixed effects model, whereas Molina and Rao used the traditional small area models for answering this kind of problems. Again, something I want to talk about. Next. Now, this is one of the earliest things, synthetic. If a direct estimate for a large area, for covering a small area, is used as an indirect estimator for this area. For example, we have all the counties in Florida. Instead, I'm trying to estimate people without health insurance. Instead of taking the county estimates, I'm taking the overall estimate for the state. Not a very good thing, but it has been used for a long, long time. The terminology, to my knowledge, was first used by the US National Center for Health Statistics. It is a wing of the, actually, I think it is a wing of the CDC. Yeah, the strong underlying assumption is that small area bears the same characteristic for the large area. The initial, some small notations, Y1, Ym, direct estimates, population size is N1, Nn. So you take the overall average, Y bar S. The weighted average, the weighted by the population size. Rather than taking Yi, we are taking the Y bar S. The idea is the synthetic estimator has less mean squared error compared to the direct estimate if the bias is not too strong. This is important because what is the mean squared error? It is the variance plus square of the bias. So even if we reduce the variance, if the bias is too high, the mean squared error can be very high and it won't serve any purpose. Fortunately, that doesn't happen much in these days with more sophisticated models. Next. The classic example, which I took, of course, from Rao and Molina by Hansen et al. So what they did, they took synthetic regression estimators, median number of radio stations. It was the pre-television era, okay? Actually, more than 500 counties in the US. So direct estimate, the median MI was obtained from a radio listening survey based on personal interviews. So that's the direct interview. And then there was an auxiliary information from a mail survey, same kind of questionnaire, single covariate in a linear regression of Y and X. The mail survey was nice. They actually said sampling 1,000 families for each county. So think about 1,000 times 500. Unfortunately, it was biased. Due to non-response, only 20% case. Now 20% would be okay, possibly as a sample size, but it could be that only several sectors of the population gave the response and the others did not. So even if it's 1,000 times 100 is a big number, that possibly was, at least they felt, it was not adequate. But still they said it is okay because the XI have high correlation with the MI. That's what it is. Next, please. Direct estimates, of course, for 85 counties were obtained through intensive interview survey. The selection was made by stratifying the population into 85 strata and only one county from each strata. Stratification is good, but then they used PPS, probability proportional to the estimated number of families. So naturally the big families actually were selected, but that possibly is okay after stratification. At least they felt it was okay. So a subsample of area segments was selected from each of the sample count areas, and families within the selected area were interviewed. And the correlation of Y and Xi was 0.70, and there are many non-sample counties, and for them they had to give only the regression, and there was no YI. So all they need was the MI hat, and that was their formula. They had the Xi possibly, but MI hat 0.52 was 0.74 Xi. The number next, please. Another example of synthetic estimation is due to Maria Gonzalez. There, I think, to my knowledge, Maria Gonzalez is the first person who coined the term small area estimation. It is a JASA paper, early enough, 73. Objective was to develop intercensual estimates of various population characteristics for small areas. They discuss synthetic, still synthetic, estimates of unemployment. Large area is a geographic division, small area is a county within the geographic division. So rather than using the county level estimate, what they did, they got UJ, unemployment rate for cell J, based on the geographic division where county I belongs, and PIJ is the proportion of labor force that belongs to cell J and county I. So just take UI star summation PIJ UJ. And they of course suggested synthetic regression estimate for unemployment rate. Also, that nothing actually, the synthetic estimates essentially are avoiding the direct estimates, as I was telling you. Sometimes it could be just a small part, the YI, in a big average, but otherwise it might be ignored, especially when you don't have a sample. Next, please. Thank you. Now, what people realized soon after, that avoiding the direct estimates altogether and getting only the regression estimates may not be a good idea. So they thought about composite estimates, which are weighted average of the direct estimates and synthetic estimates. So for example, if you have YI bar for YI, whatever you call it, for the ith area, and you have Y bar S, you will take a weighted average of YI and Y bar S. How to do that is another story, that we'll talk about some methods. So motivation was the design bias of synthetic estimators, balance that with the large variability of direct estimators. And for example, I've given a simple example, Yij, jth unit, ith area, Xij, the vector of auxiliary characteristics for the jth unit in the ith area. You take the population means Yi bar, Xi bar, that you have. Population means you don't, Yi bar, but Xi bar you have. Sample observations are Yij. So you get the Yi bar and Xi bar. Okay, so that's your sample. Next one, please. I will give you that formula, what they do. So direct estimates is what? The ratio synthetic as a ratio estimator, sorry. Yi bar over Xi bar multiplied by Xi bar. That's the estimators which you learn in our undergraduate years also. But they call ratio synthetic estimate. So the Yi bar and Xi bar, they just replaced by Y bar S and X bar S. Y bar S is the weighted average of the Y's, X bar S is the weighted average of the sampled X's. And composite estimators, the way I've written it, Ni over Ni Yi bar. That is the sum of all the Yij which you have got in the sample. You don't change that at all. For the unsampled units only, you put this synthetic estimate, but still you're not using Xi bar, you are using X bar I prime. Now you may say, how do I get X bar I prime? Because I don't know the auxiliary information for the unsampled units, but there is this trivial formula. You know the population mean for the X's. You know the sample mean, and then it is just a simple identity. Capital Ni Xi bar equal to Ni little Xi bar plus Ni minus Ni X bar I prime, and that gives you the X bar I prime. And now I will say very simple. Now, in some sense, there is no model. You're just giving a weighted average of two estimators. But Holt, Smith, and Tomerlin actually gave. Next one, model-based interpretation. Next. So what is it? Consider the model, Yij. You don't have to assume normality or anything. Independent regression model, B times Xij, sigma square Xij. So get the best linear unbiased estimator of B by minimizing double summation Yij minus B Xij square, and the solution is what I'm giving, B hat, Y bar S, and X bar S. So now you can see the new estimate, summation Yij, J from 1 to Ni. You don't change anything. And then the unseen part, summation Yij, actually over Ni, that summation Yij you replace by B hat Xij, and that simplifies to that given expression in the top. That is one of the simple example where it was implicit, but you can still think about a model justifying that estimate. Next, please. Now comes the mid part, starting essentially with Fay and Harriet. Small area models are what? They link explicitly the sampling model with random area-specific effects. This was the first time it was the Fay-Harriet, at least in the context of small area estimation. It is really a mixed model people have used for years and years, but in the context of small area estimation, I think I will give the credit to Fay and Harriet. The latter accounts for between area variation beyond what is explained by auxiliary variables. So not just the administrative records of auxiliary information, you have an area effect. We classify area, small area level models into two broad types. I said I will talk about only the first one. The first one is most well used. Area level models relate small area direct estimates for area specific covariates. And this is most of us, secondary users of survey, that's all you can get. Because unit or element level data, the micro data, is typically unavailable. So such models are necessary if unit or element level data are not available. The second is unit level model. I said I will just give the definition, but we will not talk about it. Betty Sutter Fuller is classic example. But this one relate the unit values of a steady variable to unit specific covariates. Sometimes even if it's not there, you will unit specific covariates plus area specific covariates in most examples. But if you don't have unit specific covariates, at least use the area specific covariates, but still use the micro data for the response law. And these are all model-based estimates. Next one, please. The model-based approach to small area estimation offers several advantages. I give you 5. Optimal estimators can be derived under assumed model. Now that's still a question, how good is the model? But you can do goodness of fit and other things. Area-specific measures of variability can be associated with each estimator, unlike global measures, average over small areas. That's a very important point that is often used with traditional indirect estimators. But here, you can do area-specific measures of variability. Third, they can be validated from the sample data. All the goodness of fit techniques are there, use one of them. And of course, if one doesn't work, you can entertain a variety of models depending on the nature of the response variables and the complexity of data structures. And the fifth and the final one, some people feel this is the most important one in some sense, model-based approach can still provide estimates for areas with 0 sample size. So for Florida, we have a whole bunch of counties. I can't remember the exact number now. We have sampled only a few of them. What happens? Where you don't have a sample, 0 sample size, you still can use some model-based estimate. It has some limitations, I will tell you, and people have tried to rectify it when it comes to benchmarking. I'll talk about it. Next, please. The classic area level model is Fay-Harriet. You can see that yi theta I plus ci. That's how they read it. That is the sampling model. And the linking model was theta I xi transpose b plus ui. If you put them together, which I've done at the bottom, it is a mixed model, yi equal to xi transpose b plus ui plus ei. Target is estimation, not of the b is a part of it, but really theta I, the whole thing. That's what you are interested in. So ei are assumed to be independent. There is an assumption, di are known. I'll say something about it. UIs are also IID, but the A is unknown. The assumption of unknown DI can be put to question because they're really estimates, although they have got nowadays, what is it called, generalized variance function and all that. Bob Fay's software is there. His method is there. He has another paper on that. But the problem is it is unavoidable. You cannot have both unknown. Think about it, ui plus ei. When you write the variance of yi, it is variance of ui plus ei, the whole thing. If you assume both, so you'll get that a plus gi, and you won't be able to estimate individual. So what they did, di is unknown, a is unknown. Next. Some notations, y, I denote the vector of the y's, e, the vector of the errors, u, the vector of random effects, x is the design matrix, b is the regression part, and we are assuming x has the standard linear model theory, has rank p, which is smaller than n, and we are writing in vector notations y equal to theta plus e, theta equal to xb plus u. And for known a, the best linear unbiased predictor, I'm saying predictor, I'm using the word because theta is what? Xi transpose v plus ui. You can call it estimate, but it is really a prediction because ui is a random. It is a weighted average. 1 minus bi yi plus bi xi transpose b. But look at bi is di over a plus di. V is the diagonal matrix. Now this is important. Think about it. If the sample variance is very large compared to the model variance or prior variance, Bayesians will call prior variance, the BIs will go to what? BI is very large, go to 1. Then the 1 minus BI is getting close to 0. You better rely on the regression estimate because sample variance is very large, very unreliable. If opposite is the case, if the model variance is very large compared to the sample variance, then the regression part disappears, you better stick to the direct estimate. But this weighted average is actually the kind of ideal solution. If we assume normality, it is even the best unbiased predictor, BUP, then you don't have to restrict yourself to linear models. Next one, please. There is an alternative Bayesian formulation. In fact, Fay-Harriott wrote it that way. Yi given theta I, normal theta I di, theta I given b, normal xi transpose b a. The Bayes estimate becomes exactly the same as BLOP. If instead we put a uniform prior for b, the Bayes estimate, this is not BLOP because xi transpose b I wrote, but you have that b tilde or b hat, whatever it is. If instead we put a uniform prior for b, the Bayes estimator is the same as the BLOP. Now, in practice, A is unknown. Carl Morris did not talk about small area. He was talking in general of mixed models. He put the prior pi of BA equal to 1. But otherwise, Fay-Harriott didn't go along that route at all. They estimate A to get the resulting empirical Bayes estimate and solve iteratively the two equations. It is purely a moment-based approach. First of all, if the V, which is the diagonal di plus A, is known, then the B tilde is the BLOP. But you don't know the A, so what they did, they computed the expectation of the residual, which is summation yi minus xi transpose b tilde square over di plus A. Expectation is m minus p, and now they put the method of moment estimates for m minus p. It has this problem, you can get negative estimates of A, then you force it to be 0, etc., etc., etc. People have other options, I've mentioned some of them, but I will stick to this one. Next, please. Fay-Harriott iterative method may not be too convenient for analytical studies. In fact, this is one of the, again, become a very, very classic paper. J.N. Kirao and his students in J.N. Prasad, they suggested an unweighted least square estimate. It is not the best estimate. So what you do, estimate B, just least square, x transpose x inverse, x transpose y. You have everything. The V involves the di plus A is unknown. You avoid that. Now compute the expectation of xy minus xi x beta L hat square. which turns out to be that form. The Ri is what they call influence functions, possibly for excise, and then estimate AL hat just by using the method of moments. As I said, the limitation is it can be negative, then you force it to be 0. Not good, but so BI hat hell is given by DI over AL hat plus DI, and then do the same thing actually, but then when you're estimating the regression parameter, you are taking the V, but instead of putting A, DI plus A, what you are doing, you are using the AL hat rather than the original Fay-Harriet estimate of A. So AL hat is the only change. Next, please. Prasad and Rao found an approximation that was one of the classical things. Again, mean squared error of their E-blob is also empirical Bayes. The Bayesians will call it empirical Bayes, possibly. The thing is, take the subjective prior, normal Xi transpose BA, the Bayes estimator I gave, and write the theta I hat tilde EBA as given by this, B tilde A. This is the blob, but A is assumed to be known. And now plug in AL hat. So BI becomes BI hat L, A becomes A hat L, B tilde AL hat. The interesting thing is with their method, and that is not the only their method, there are some others I'll mention, you can break up the mean squared error into 3 pieces. The first term is the Bayes risk, if you want to call it theta I minus theta I hat B squared. The second term is the additional uncertainty due to estimation of B when A is known. The third term is the extra uncertainty due to estimation of A. And that is valid for Prasad Rao because of the estimate that they put. But that is not just Prasad Rao, others also have got it. Next one, please. So now the first one, DI times 1 minus BI, that you can calculate explicitly. Second one, also G2I you can calculate explicitly. The third term, you cannot compute explicitly. You go up to the second order approximation, which is G3I. The first term is of order 1. The second term is of order n inverse. The third term is also order n inverse. So what Prasad Rao said, an estimator of the MSE correct up to order m inverse. Somebody might say people got surprised when it first came, but they were very clear. People thought it would be just G1I A hat plus G2I A hat plus G3I A hat. You can see instead of G3I A hat, you have a 2 there, 2. Why that 2? Because if you calculate expectation of G1IA hat, you get G1IA minus G3IA, and then the next order term is small. So you have to include the G3IA hat, add to G1IA hat, and that's why the 2 G3IA hat. Now there is a further appointment. One of my best students, Gauri Datta, with John Rao, and Gauri's student, Smith. Next transparency, please. I'll give you an example. The US Department of Health and Human Services provides energy assistance to low-income families, and the eligibility is determined by a formula where the most important variable, an estimate of the current median income. Okay, families by states, 4-person families. The Bureau of Census is doing that informal agreement to the Health and Human Services since the latter part of 1970s. Their methods were not very good, but what Fay, it was another paper by Fay. So you have the sample estimates of the state medians for the current year. States are here the small areas because the original survey was carried out at a national level. And also they put the adjusted median income. So C is the current population survey, current year sample estimates, CPS. The adjusted census median is the base year, recent most decennial census, but multiplied by the ratio a Bureau of Economic Analysis per capita income in the year C to the base year B. I thought it was overfitting, but apparently it did well. So they used not only the base year census median, they used the base year census median multiplier with this multiplier, BAPCI, actually, the ratio from the C to B. Next, please. Following the suggestion of A, actually we did census median for the as a second independent variable, compared the EB estimates, CPS estimates, the Bureau of Census estimates against the 1979 census estimates. Why 1979? I'll tell you. Because they assume something is a gold standard, the census figures, although they are still estimates. So 1980 census only gives you the estimate from 1979. From 1979, you have the current year estimates, you have also the census estimates from 1980, and the census estimates from 1980 are used as the gold standard. So, okay, so that is the gold standard. So comparison was based on 4 criteria. There was a panel, I was not there at that time, on small area estimates of population income, the National Statistics average relative bias. EI is the estimate, EITR is the truth. In our case, it is the 1980 census figure, the gold standard, divided by EITR, then average squared relative bias, average absolute bias, that's self-explanatory, average squared deviation. Next slide, please. And you can see that the empirical base is beating everything. You can all along quite a bit. Relative bias, squared relative bias, everything. Absolute relative bias, say for example, you take average squared deviation, 8.36 of course in certain units. Sample median is 16.31, and that is the previous estimates, the Bureau estimates based on the previous approach, and the empirical base of FAE, which we adopted, is giving us this answer. We did also some hierarchical based very similar results here. Next one, please. Just a few concluding remarks about the model before we go to benchmarking and others. There are other refinements. Partha Lahiri, another of my famous students, with J.N.K. Rao in JASA 1995, avoid the normality assumption of random effects, but assumed instead 8th moment. Then Gauri and Partha, that's a very important paper, Statistica Sinica, very well cited. They got maximum likelihood and residual maximum likelihood. And then there are several papers, Kullan Das, one of Calcutta University fellow, Jiming Jiang, John Rao, etc., etc., etc. There is a whole bunch of papers which did that. But let's proceed. Next, please. Just quick comment, general exponential family. I tried that. Possibly we had the, no, some others did for the binomial, but we did it for the general exponential family in 1998 JASA paper. Say, for example, if you go for Bernoulli data, say people without health insurance, with or without health insurance, that kind of situation, you take the logit, model the logit, Poisson, it is a log linear model, you model the Poisson rates, model the theta is always for the canonical model, the canonical parameter. And alternately, you can use gamma beta priors for the PI, gamma priors, and so on. And Nanak et al. Actually had an example binary data. Next one, please. There is another thing which has come up recently, more recent. It is called, because I'm getting out of time, I will just skip that. It is called actually observed best predictors. You can take a look at it, another JASA paper, but let us move. Next one, please. Benchmarking. Yeah, this is a very critical issue. People realize that in the 90s and now it has flourished. The model-based estimates, when aggregated, may not equal the corresponding estimate for a larger area. On the other hand, the direct estimate for a larger area, a national level estimate, is quite reliable, typically quite reliable. I would say typically is a good word. The matching the latter may be a good idea, for instance, to protect against model failure, very often for political reasons. I remember once I was actually working on a survey, again, health and people with or without health insurance, but only within the state of Florida, where I belong. So we did actually, this time I was involved in designing the survey as well with some of my colleagues. But what happened, so that was for counties. So it was fine. Not even counties, 17 geographic regions. Then the next year they say, we want the same kind of estimates for census blocks. We had 17,000 data and 9,000 census blocks. So you can imagine what will happen. Most of them will be just zero, right? So that is the political reason, but protection against model failure. So suppose theta I will just formalize, is the ith area mean, theta t is the weighted overall mean, the weight, the wj may be known, population of units in the jth area. So direct estimate is wi theta I hat, which won't equal the model-based estimate. In order to address, people have suggested, actually the people, when they asked me at that time, I did not know anything about benchmarking. My knowledge about benchmarking came much later, about a decade later. We're talking about late 90s. So they asked me what to do. It is not matching. And I said, okay, very simple. Just do the ratio adjustment, which I'm giving here. And they're really happy because eventually everything matched and nobody is going to challenge them because they match for the whole, all the 17 regions, matched for each one. It was great. And they're even ready to pay me for it, believe me or not. And some people use different adjusted estimators. So if you multiply by WI and add it up, you can see you are getting the overall estimates. But people have done better. When I learned benchmarking, really, I found we can do a lot better. Next transparency. Next slide, sorry, please. One criticism against such adjustment is a common adjustment is used for all small areas, regardless of their precision. Now the researchers came. I think it started with Danny Pfefferman, but then we got into Wayne Fuller. That was quite interesting. He put, these weights are not necessarily the WJs. It could be anything, PJs, specified weights. And you'd use the subject to the constraint. The WJs and PJs don't have to be equal. And then they got the resulting estimate, the BLUP. But you can see now, for the ith area, you are not just taking the direct difference or direct sum. There is a multiplier, lambda I. And they gave a formula for lambda I. Got a similar formula. Gauri, myself, my students, Rebecca Stokes and Jerry Maples of the Census Bureau, we took a general Bayesian approach. The advantage was we didn't have to assume anything, no normality, anything. Give me a set of Bayes estimates, we can immediately produce the benchmark estimate. And that estimate looks similar, but the lambdas are actually very same, believe me or not, depend on the W's, but these estimates are different because it is not BLUP, it is just a general Bayes. It is a much more general. It could be hierarchical Bayes, whatever it is, empirical Bayes, whatever it is. So that is one thing. These are some of the recent work. Next. The approach of Dr. Ghost-Maple extend to multiple benchmarking constraints. We have a biometrica paper with Bill Bell. I have one with Gauri, which extend the work of Wang, Fuller, and Chu. And situations also one needs two-stage benchmarking. This is one example I will tell. National Agricultural Statistics Service, it is a part of USDA. I was doing consulting for them for about 2 or 3 years. Now they need the dual control of matching the aggregate of county level cash rent estimates to the corresponding agricultural district comprising of several counties level estimate. This is all for agricultural lands and all that. And the aggregate of the agricultural district level estimate to the state level estimate. So states are the big thing. States are not small areas. State is the kind of gold standard. But you have to match at 2 stages. And Emily Bird, Bill Cesare, they are both at that time with the NAS. They're both left. Emily is now a faculty at Iowa State. Will works for the Westat. The Andrea Ursulescu, she is a student of Fuller. She is also with Westat. Myself, we have a recent paper, as you can see, adopted an approach which we first, Rebecca and myself, Rebecca Stokes, who did apply it to the NAS problem. Next. And we did some second order unbiased MS estimates. They are not typically available for ratio adjusted, for different adjusted. We did that. We have another paper in Statistica Seneca, also a part of Rebecca Stokes' dissertation, which we, all you have to do, put another term, because it cannot be the best, the MSC of the model based, because you are adjusting. And we got that extra term and estimated it. And that's what it is, because that is also of order M inverse. And that was exactly what it is. So what do we do? Next. Now comes something which I've been working quite a bit recently. I will tell you. A different but equally pertinent issue has recently surfaced in the small area literature. This concerns the need for random effects in all areas, whether even fixed effects models should be adequate for certain areas. Possibly this is one of the few papers of Peter Hall. Peter Hall usually did not get into small area, obviously, not even random effects models, but this is one of them. I think he has done a couple of other work with Papabrata Maiti. Gauri Datta, Peter Hall and Gauri's colleague Obbuday Mandal, first to address this problem. And Peter, being a classical statistician, suggested a preliminary test-based approach. Testing the null hypothesis is the common random effect variance was 0. So use a fixed effect model if you accept the hypothesis. Use a random effects model if you reject the all or nothing kind of approach. Not very good one, but still published in JASA. Gauri said it is because of Peter Hall, but anyway, that's what it is. This amounted to the use of synthetic or regression estimates upon acceptance of the null and composite estimates, weighted average of direct regression estimates otherwise. But Gauri and Obbuday realized the problem. Next, please. The Datta-Hall model works well when the number of small areas is moderately large, but not necessarily when it is very large. And that's what happened. At a state level, that 50 states for the District of Columbia, the null hypothesis of no random effects is very likely to be rejected, primarily due to a few large residuals causing significant departure of direct estimates from the regression estimates. The example which Gauri and others took, it turned out Massachusetts is the state which is pulling everybody up, so the hypothesis was kind of rejected. Few large residuals, that's it. And Massachusetts, in that case, was typically the one. There are a couple of others, but Massachusetts was the primary. So what they did, they put spike and slap priors, very popular now. Put a positive mass at 0, resulting in a spike at 0. Slap part they used is a normal distribution, 0 means. Not my favorite. Normal is a light tail distribution. Common unknown variance across all small areas. The approach amounted to what? I earlier wrote UI for the random effect. Instead, you take delta UI for the random effects. Delta I and UI are independent, and delta I are IID Bernoulli. UI is still the same. So either take actually 0 with some positive probability or keep it as such. Next. That actually sparked my interest, and I asked my student, Xing Tang, at that time I was also actually in SAMC. I also asked Ning Jo Ha, who was a postdoc on myself, and Joseph Rance, considered a different class of priors, meets the same objective but uses absolutely continuous priors. Much easier to implement, believe me or not. Nowadays with Markov chain Monte Carlo, it was a piece of cake for these people. for Xinjiang, who implemented it. These priors allow different variance components for different small areas, intended to capture local small area effects better than the priors of Dutt and Mundell, who considered prior variance either zero or common across small areas. And particularly useful when the number of small areas is very large, when considers more than, for example, 3,000 counties, and one expects a wide variation in county effects. And the proposed class of priors called global local shrinkage priors, I will just mention that this is important, not just for small area estimation, for the people who are interested in the analysis of sparse data, this is one of the simplest things to implement. Next, please. Carvalho, Paulson, and Scott started this, also Paulson and Scott. They're scale mixtures of normals. We are using what? Capture potential sparsity. In our case, it means lack of significant contribution, but many of the random effects. By assigning large probabilities to random effects close to zero, but also identifying random effects which differ significantly. And two levels of parameters. Definitely. The local shrinkage parameters act at individual levels, and the global shrinkage parameter is common for all random effects. Fay-Harriott, just only one global parameter. Gauri and Abhuda, the variance para is either zero or common across all small areas. We don't need that. Next, please, we'll give our model. The random effects UIs have now 0 lambda square A. Fay-Harriott only A. Gauri and data, it is still a common. While the global parameter A tries to cause an overall shrinking effect, the local shrinkage parameters lambda is controlling the degree of shrinkage at the local level. So you can even get, doesn't have to be zero, you can get the area level effects actually. If the mixing density corresponding is appropriately heavy-tailed, that's what is important. Large random effects are left almost unshrunk. And this class of global local priors includes the 3 parameter, there is a whole class of priors. This is a very current literature, not just for small area estimation, but for analysis or handling of sparse data in general, microarray experiments, image analysis, whatnot. Next, please. We are almost at the tail. Sorry if you bear with me. One was estimate 5-year county level overall poverty ratios. So 31, 41 counties in the data sets, covariates for food stamp participation, and we got that result. We got quite an interesting thing. Poverty ratios are very small for a certain county, like one county in Texas, very high for a county in South Dakota. The median was 14.7. Mississippi, Georgia, Alabama, and New Mexico, 55% plus counted had poverty rates bigger than the third quartiles, which is 18.9%. Whereas New Hampshire, Connecticut, Rhode Island, Wyoming, Hawaii, New Jersey, 70% of the county had poverty rates less than the first quartile. That's quite interesting. Next, please, just the picture. This is just the picture. Let's not go there, and let's go to the final topic. Next, please. This is I'm currently working on with my colleague from Japan, Masao Hirose, and my student, Tamal Ghosh. Tamal just finished his PhD, of course, last year, but we are working on that. The normality assumption can be justified only after transformation of the original data. Then one performs analysis based on the transformed data, but transform back properly to the original scale to arrive at the final conclusion. A common example is skewed positive data, income data. We all know log normal is a good one. Gets a closer normal approximation, and this stuff started by Eric Slat and Tapabrata Maiti, JRSSB, and myself and Tatsuo Kubakawa of Tokyo University in 2015, Biometrica, providing final results for back transform original data. Next. For example, consider a multiplicative model, yi, phi I, 8i, with zi log yi, theta I log phi I, ei is log 8i. Then use the Fay-Harriott model for the zi's once you have transformed. And you get everything for the theta i's. But think about it. You are not interested in the theta I. You are interested in phi I. And most people think all you have to do just exponentiate. That's not right. If you assume a log normal distribution, if you just use exponential theta I hat b, you are including a bias, and that bias is given by that. So instead of using exponential theta I hat b, you have to estimate the whole thing, the bi hat as well. You have all the estimates, no problem, based on Fay-Harriott, but you have to use this particular formula to avoid bias, actually. Next, please. Another interesting, that's what we are working on. IID, binomial NIPI, we use the Erskine transformation, then start with ZI, normal theta I. The Erskine transform has an advantage. The DI's are gone. You have something known, 1 over NI. And now use normality, approximate, but good Taylor approximation. Theta I is sine inverse 2pi in 1. Most people don't know it as sine inverse square root of pi, but these two things are linearly related. There is a known constant. So do the back transform, and now the analysis becomes much more complicated because you have to manipulate all this sine theta I. Same thing about Poisson, y half normal theta I. An added advantage here, the assumption of known di, which is really untrue, can be avoided with this kind of transformation. Next, please. The final thing, the topics have covered only a small subset of what people know. For example, we have not talked about design consistency. The sample surveys are typically design-based, simple random sampling, stratified, cluster sampling, multi-stage sampling, so on. Spatial space-time models, measurement errors. I've done a little bit on some of these areas, but not all. Poverty counts for small areas, empirical-based confidence interval, robust small area estimation, misspecification of linking models, etc., etc., etc. There are so many of those. That's what it is. Thank you very much for your attention, and I'll be very, very happy to answer questions. Please go ahead. So chat box is there.
We would like to express our sincere thanks to Professor Ghosh for taking time out of his schedule at such a short notice and giving us such a wonderful exposure on small area estimation. We'll now have a short question and answer session. I'll request the participants to write their questions to the speaker in the comment box only.
Any questions?
Any questions? Okay, so sir, we have a question from Vijay Kumar.
Good.
And he asked that how we use small area estimation to estimate disease prevalence.
Prevalence, yeah. That's a very interesting issue, actually. We have to extend the models. I have done a little bit with a fellow now in Emory, at that time was in Minnesota, Lance Waller. Spatial models. This is what is very important. The disease prevalence and all that, for that kind of thing, spatial models have found to be very, very useful. So what you have, instead of just an UI, you have to add another effect VI, or if you don't want to use just one random effect, you use the UI. The UI are correlated. For example, a county I is correlated with its neighboring county or other counties which have similar characteristics. So basically, instead of UI independent normal 0A, we used a special model. The data we had was the disease prevalence actually. We're talking about cancer at that time. And we used a special model, used the neighboring geographical areas, and it was something to deal with many, many years ago. I'm thinking about at least 16, 17 years ago. But a special model, that is the one I remember. Near, I think, if I recall, upstate New York, near Syracuse and Ithaca, those places. Right, Cornell is located, Syracuse, Ithaca. So there, instead of UI independent, just normal 0A, use a special model which will build a special correlation between the UIs. So that is what I know. There may be more sophisticated analysis which I'm not aware of. And there are people who are doing that. There is a group in England who are doing quite a bit. They have the space and time spatio-temporal.
Sure, can we help here remote sensing data through?
That is always helpful. The remote sensing data have been used by
for a small area estimation. Just like I working as a Rajendra Modi Research Institute of Medical Science, here data gathering for Kala-Azar disease, which is previously known as visceral leishmaniasis. There we collect the data through remote sensing.
Correct.
Yeah.
Okay. Now,
how we use a small area estimation here, sir?
People can still use that. For example, USDA, I mentioned briefly that they've been using it for a long time, but now it is more sophisticated. They're using the satellite data to estimate the area under the most two important crops in this country, at least in the Midwest, are corn and soybean. Area devoted to corn, area devoted to soybean. They use the satellite data as well as one individual in-person data. Finding the British Center did that earlier, but that was a very simple model. A mixed effect model where you have a unit level random effect, also an area level random. Nowadays they're using, I think, to my knowledge, special models. Arthur Lahiri and others, the USDA people, they're using a special model to address this kind of problem. Yes. So this is an interesting.
Okay, thank you, sir.
Special models are being used for small area. The main thing is that instead of you can have both UI and VI, but even if you have one, if you call it UI, these UIs should be correlated. The neighboring area or whatever relevant doesn't have to be, or in your case, the remote sensing. The remote sensing data they used as auxiliary variables, actually. The USDA people, I think that's what they're doing. They're using a special model, extending Betty, Sutter, and Fuller. But like Betty, Sutter, and Fuller, they're using the satellite data as auxiliary variables.
There much auxiliary information also available. Yeah.
Yeah, they had. There are some papers out, I'm sure. The person who works with them, who may be easily available, other people also will be available, is Bal Nandram of WPI, the Worcester Polytechnic. Bal does exclusively smaller estimation since his PhD dissertation. And
sir, can we generalize a small area estimation for large areas, as like if we collect data from one district in Bihar, Patna, Then we generalize the data for whole Bihar state in India. Can we generalize it?
That I doubt very much. There are large area. Okay.
As different area have different geographical condition and
different
many more
different areas
situation.
have variability. Different areas have different variability. If we just take one and try to project the rest, it could be a very dangerous. Rather than take all the areas and see the area level effects. Some may be insignificant, some may be significant, but you can still take it. That's what it is.
Yeah, this problem, some may be significant and some not significant.
Yeah, that's how I talked about this global local priors, which we are doing. Gauri and Abuda had spike and slab, which is also good, but this global local thing is working very well. And I think other people have started using the global local also for smaller estimation, so that all areas are taken into account, but there should be two components. The various components comprises of two parts. One is the local area effect, which varies from one area to another, and the one is the global effect, which is common across all areas. The global will try to push everything into one, and that is the danger. Like everything was pushed towards Massachusetts in Gauri and Abdullah's example, whereas the locals will pull the real ones. That's what.
Thank you, sir. Okay, thank you, sir.
Most welcome. Any other question?
Sir, can I ask one question?
Sure.
Sir, albeit being a naive point of view, I would rather be actually grateful if you could recommend any book, especially considering myself from a postgraduate point of view. I would be very grateful if you pinpoint those prerequisites which we need in order to study in at least some intro level, because I found that topic very fascinating from your lecture. So I'd be rather very grateful if you could pinpoint or recommend any book for the introductory level, at least to give intuitive angle to this topic.
I'll give you the second edition of J.N.K. Rao's book. That's the classic. Everybody refers to it. J.N.K. Rao and Isabel Molina.
Yeah.
If you send me Rao and Molina, that book is available, a Wiley publication. It has been out already another 5-6 years. The second edition. First edition appeared in early 2003 or something. The second edition, it starts from a very it is a little bit difficult at some points because, for example, I'm using Rao and Molina. The initial chapters are very good. That gives you the flavor, the best. It was super. The very first few chapters. And then they tried to put everything in a very general format. For example, when you talk about a random effects model, I was just using what? A random area effect. Instead, they will use capital Z times U, a very general, so that the method for actual application, what I was saying is good enough. But because they sometimes try to write everything in the most general framework, the notations become fairly complex at the end. But that's not a problem. The basic problems and the basic methods, first few chapters, just read it, you'll be able to grasp it, even with a postgraduate background. That's very simple. So that is the book I recommend everyone. J.N.K. Rao and Isabel Molina.
Thank you, sir. I'm very grateful for that. Thank you, sir.
Most welcome.
Thank you, sir. And with this, we come to the end of the first series of lectures in this lecture series. May I now request the convener of the Outreach Program Committee of CSA, Dr. Sumanto Addo, to share a few words.
Thank you, Dhiman. As a convener, it has been our pleasure to host this virtual lecture series. I am thankful to all faculty members, research scholars, and special students for attending the lectures. We have been fortunate to have three very senior eminent statisticians, Professor Shama Prasad Mukherjee, Professor Bikash Shina, and Professor Malay Ghosh in this series. I am grateful to them. I am very much thankful to all the senior members of Calcutta Statistical Association for their generous support to organize this lecture series and keeping faith on us. I also want to thank our president, Professor Monisha Pal, our secretary, Dr. Dhiman Datta, and the members of the Outreach Program Committee, Dr. Arindam Gupta, Dr. Tuhin Subra Bhattacharya, Dr. Hare Krishna Maiti, and Dr. Saptarshi Mondal. I also pay gratitude to late Professor Aditya Chattopadhyay, who was instrumental for this online lecture series. We lost him few months earlier. It is a huge loss for the organization. I am sure that the students must have some idea about diverse applications of statistics to solve real-life problems by attending these online lectures. We will continue this lecture series in future. We now take a pause and have a plan to resume it from August end or early September this year. I once again thank everyone and at the same time apologize for some technical problems that occurred during this series. Please take care of yourself during pandemic. That's all. Thank you.
Thank you, Dr. Anto. We thank all of you for joining us today. Looking forward to meeting you in the next lecture, which will be announced in due course. Let's keep on propagating statistical knowledge. Goodbye and stay safe. Thank you.
Thank you, Professor Ghosh. Thank you.
Thank you. Thanks everybody. Thanks for attending. And my tribute to Aditya. He was such a good friend. I'm very, very sorry to see him go like this. Oh, that's terrible.
Thank you.
Hello, Molaida. This is Suhash from Pensacola. I enjoyed your talk. It is a fascinating area. Yeah, it was very good. So we stay in the same state, but we never see each other. But yeah. Okay, thank you.
Pandemic
Yeah.
host koro, amra host kori the chapter meeting যাতে লোকে আসতে পারে।
হ্যাঁ সেটাই করতে হবে, হ্যাঁ, right. We can do that, yeah, sure.
ভাই এখন টাইম পাচ্ছে, তাই তো?
হ্যাঁ